Well, hello and welcome. As some of you may know, waste heat is the world's largest untapped energy resource, so let's explore how to go after it. Welcome to this second of four webinar series designed to help manufacturers improve energy performance and achieve high return on investment energy savings. Today we have four expert presentations on heat recovery, followed by a Q&A session. My name is Jared Leake, and I'm the CEO for the Australian Alliance for Energy Productivity, or A2EP is, of course, much easier. As always, I'd like to start with an acknowledgement of country and acknowledge the traditional custodians of country whose connection to country certainly inspires me. This webinar is brought to you today by our more than 90 A2EP members, which has a broad cross-section of energy industry leaders who share our mission to decarbonise and improve the energy productivity of our industrial and commercial sectors. Just a little bit of housekeeping. This session will be recorded and we'll have those slides out to you with the presentation recording early next week. And if you have some questions today, please pop that in the Q&A box down the bottom, or feel free to have a bit of a sidebar chat using the chat function. As mentioned before, this is the second in a series of four webinars on saving energy and manufacturing. We thought this is a great way to lead into our Renewable Heat Conference next month, which will showcase technologies to eliminate fossil fuel usage, but typically require investments for electrification or an increase in costs for fuels such as biomethane. So what better way to offset those costs than reducing the amount of energy used in the first place? Last week we did steam reticulation systems. Next week we're going to look at the steam boiler optimization, and after that metering and monitoring. But today it's all about heat recovery, and one that's close to my heart after spending 20 years at Alfa Laval, one of the biggest energy efficiency and heat exchanger companies that most people haven't heard of, unless you're in the process space. And whilst at Alfa Laval, actually, we added up the heat recovery installations around Australia, and it came to some about 3 gigawatts, which is about 10% of Australia's usage for process heat. And that excludes HRSGs, which is used in combined heat and power plants. And that's probably another 10% or so there. So heat recovery is already doing a lot, but there's definitely more to do. On HRSGs, I thought I'd quickly share with this one that was out in LinkedIn today. They're from Evo Energy Technologies, doing a beautiful HRSG. It was coming from 3 by 1 megawatt cogen systems for Simplot in Bathurst. Beautiful little project. We're not talking too much about HRSG. We're talking about a whole range of different opportunities here today, but that is a great example of heat recovery right there. Joining me today, we've got Mark Barber, A2EP's membership manager. Having spent decades, or years, let's say years, Mark, of energy consulting and resource recovery. Mark, heat recovery opportunities, I guess you've seen a fair few in your time, and you've seen a lot of heat being displaced or sent out to a cooling tower, even though there's maybe a boiler right next to it that could be using to preheat some of that heat instead of going to a cooling tower. You've no doubt seen a bit of this in your time.
Absolutely, Jared. It's unfortunately that is the case. That so many times walking through a plant room and through a site and seeing good quality heat being dissipated nearby other systems that could be using that heat, it really breaks my heart. And but the good news is we're about to hear a succession of great actual projects that have been implemented with some details around that. So you're in for a treat.
Beautiful. And Mark, why don't you take us through our speaker lineup here today? We'll get cracking.
Yes. So we've got it's jam-packed agenda with Alan from EnergyLink Services, Elsa from TLV, Nick from Windsor Engineering, and Anson from Alfa Laval. So just a little bit of info about Alan. Alan is an associate director with EnergyLink Services and an energy consultant with oodles of experience in industrial energy efficiency, renewables, and carbon strategy. He's a certified energy manager, CEM, and a CMVP, and is known for his work generating VEECs, ESCIs, and ACCUs across various projects and sectors. And worth noting that Alan was a recent winner of EEC's annual award for Best Industrial Energy Management Project. So over to you, Alan.
Thank you, Mark, and thank you, Jared. Good afternoon, everyone. My name is Wang from EnergyLink Services. It's great to be part of this A2EP webinar series. My work focuses on energy and carbon abatement advisory and projects across multiple industrial sectors. And heat recovery is one of the most practical areas we help clients unlock savings for. So today's session is about unlocking value through heat recovery and measurement, how we can reduce energy use, cut emissions, and access incentives like fix by turning waste heat into a valuable resource. So why it matters? Just on the next slide, heat recovery is one of the lowest hanging fruits in industrial energy efficiency. We often see untapped opportunities in flue gases, boiler blowdowns, condensers, and even HVAC systems. The benefits are threefold. So you're looking at lowering your energy costs, reduce your emissions, and also access to incentive schemes like FIX in Victoria, ESCIs in New South Wales, and sometimes even ECUs everywhere in Australia, depending on the scale of the projects. So let's look at some of the typical opportunities, which if you look at the next, it's on the boiler flue gas economizers. So in natural gas fired boiler, if the flue gases exit around, say, 180 degrees Celsius to 200. By installing an economizer, you can recover a portion of this waste heat to preheat the boiler feed water, raise the boiler feed water temperature. Depending on the application, this can then reduce fuel consumption by 5 or sometimes even 15% in some extreme cases. And in larger systems, that could mean several hundreds gigajoules saved per year per megawatt of boiler capacity. Second, you've got the preheating combustion air. So this involves the raising of the combustion air temperature from ambient temperature, say, roughly around 20 to 25 degrees Celsius to 80 or even up to 120 degrees Celsius by capturing heat from the flue or the boiler casing. So every 20 degrees Celsius increase in combustion air temperature can improve boiler efficiency by roughly about 1%. In practice, we could deliver about 2 to 4% savings on fuel use, depending on the boiler design control systems. These are all those simple retrofits that often have really quick paybacks, particularly when the fuel costs are high, or if you can actually tap into incentive schemes like the fix. And number 3, we've got the boiler blowdown, which is another major opportunity in steam boilers, especially operating, say, 10 to 15 bar. Blowdown water could be discharged at near saturation temperature. And instead of venting this energy, we can recover it through a flash vessel, generating low pressure flash steam, say around 3-4 bar, which can then be reused in other process or heating loops. This will then reduce energy losses from the blowdown. Condenser heat recovery will be especially relevant in refrigeration or vacuum systems. So condenser water might exit at, say, 30 or 40 degrees Celsius, and while it's low-grade heat, it can then be repurposed to preheat water. For example, boosting hot water inlet temperature, and then with the right heat exchanger, this can then offset some gas or electricity heating loads, mostly gas in this particular case, and this will be quite relevant in the food and beverage sector, where there's a high cleaning or processed water demand. We've actually put together a table. So here's a table that we'll put together to guide you through typical heat recovery options and the savings ranges you might expect, and obviously together with the sources that made those claims. It's meant to help you benchmark your own site or your upcoming projects. The A2EP team will distribute the slides after the webinar, so you'll be able to refer this to in a bit more detail. In this case, I'll skip it for a bit later. So why good measurement matters? So in order to capture this additional value, especially in terms of verifying the actual savings and access incentive schemes, accurate measurement via, I would say, fit for purpose metering, and also make sure the meter is calibrated is the most critical. It verifies your saving and supports your internal investment decision making. If you think about this, if you have no data, there will be no certificate revenue generated from the savings estimate, because you can't really verify the savings. In turn, there will be no investment decision. So if you have good and reliable data, then you can unlock what we call bankable savings. There are some best practice principles you can refer to. So for example, measurement needs to start with clear project boundaries. You want to isolate only the systems affected by the heat recovery project, but you don't want the boundary to be too big or cover too many things, because the verified savings will then be, maybe then will be insignificant within a boundary. It will then be difficult to verify what the real saving is, and also be adding uncertainty to the savings accuracy. We'll discuss this a bit more in detail in the case study later. So secondly, you want to establish a robust baseline. You want to adjust for variables like production or seasonality, and then you want to use meters that are fit for purpose, as I mentioned just earlier. You want to look at steam flow meters or temperature sensors. You want to install them early to capture both the before and after data, so you can then compare apples with apples a bit later. So even with perfect planning, challenges do happen, which is if you look at the data challenges or metering challenges, which is on next slide, you will see meters can fail, especially say steam meters. Data logs could be very noisy. The baseline, maybe wasn't captured in time, so you don't have a proper baseline. You don't have like enough time period to capture the full seasonality of the baseline, full production cycle of the baseline. We often work around this by using proxy indicators, like equipment runtime, production output, or raw material that's being used, or you can correlate with utility data. But then it would then require justification. So we obviously want to maintain a data gap log to track any adjustments, so you can transparently claim what's being adjusted through your model process. So if we move on to the last slide, if we look at the real example, in this case for McCain in Ballarat, they're in the process of implementing a project to recover high pressure condensate from their boiler system, which includes a 25 megawatt boiler. So it's actually quite sizable. The goal is to reduce flash steam losses and minimize the energy required to heat the cold makeup water. And they are looking to reduce the steam pressure from 15 to 4 bar, capturing flash steam that's currently fanned through the low pressure condensate atmospheric fan tank, which is, you can see this in the screen on the right bottom. The recovered condensate is still hot and will be returned to the boiler, which will then reduce their natural gas demand. In this case, we'll plan to use the IPMVP, which is the International Measurement Verification Protocol, option B, with all the parameters being directly metered, providing a highly robust basis for savings and certificate creation, in this case for fixed creation down the track. If you look at the natural gas boundary marked by the red dotted line, you'll see that it's actually defined quite tightly. This means we rely on natural gas submeter to provide accurate gas usage data. You obviously need to make sure the meter is calibrated. In this case, according to the meter spec, it's once a year. So there's additional costs you have to consider. And then the fallback option will be use the site's main gas income meter. But that also presents challenges, because the savings will then be less than 10% of the total site consumption, which will then be difficult to distinguish what the real saving is from the normal usage variation. And sometimes we call it noise. In this particular case, the results may appear insignificant or be dismissed as noise completely. So that's why you want to avoid it. You want to set the project boundary properly, which is the most critical. It directly affects how measurable and credible your savings will be. So looking at the project delivery, it will be delivering about 18,000 gigajoule in annual gas savings, which translates to about 8,000 tons of CO2 abated over 10 years, which through the fixed schemes, you'll give you about 8,000 fixed for creation of 10-year savings through the VU schemes. So on the fixed value, if you look at today's fixed price of say $100 per fig, the project stands to recover about 750 to 800K in certificate revenue after fees and charges. That's the end of my presentation. Thank you for your time, and I'm happy to take any questions a bit later.
Yeah, wow, that's quite some savings there, Mark and Alan. Wow, and quite some Veeks generation. That's got to have a hell of a return on investment, that project.
Nearly $1 million rebate from the VEEK scheme. That's impressive.
Yeah.
Thank you, Alan. And I'd really like the point you made too about the value of M&V, even if you're not claiming certificates for these projects. The value of doing a formalised M&V, putting in proper metering, doing a baseline is just an essential task anyway to verify the outcomes of a CapEx project. The next speaker is Elsa from TLV. Elsa is a consulting engineer with TLV International, responsible for improving the efficiency, reliability, and productivity of steam systems. Elsa surveyed and studied many, many systems across the globe. Over to you, Elsa.
Thank you very much, Mark. Thank you, Jared. Thank you to A2EP for allowing me to speak in this webinar. Thank you to all the attendees. Really interesting hearing Alan's presentation there and some of the crossover as well. And it's always good to see we're presenting a common message about heat recovery solutions. TLV is a Japanese company, and we focus on the steam system. So hoping to give some case studies today in terms of good ideas, low-hanging fruit, areas where we believe you should start in your energy recovery journey within the steam system. So common discussions we have with members on site often lead to these some of the regular issues that we hear when we discuss the steam system and issues that customers may have. So first of all, just looking at the boiler system, a very common situation, particularly in your smaller general industry plants, is that the boilers, the plant knows their steam equipment very well, very clearly, and they know that their steam equipment maybe needs 8 tons of steam per hour. But when they look at their boiler flow meters, they're always noticing, okay, our boiler's generating 9 tons, 9.5 tons pretty consistently. They're wondering where is that extra 1.5 tons of steam going every hour? Very common situation. And beyond that as well, engineers and non-engineers on site can see steam vents coming out of maybe condensate return tanks, boiler blowdown tanks, and they're unsure. They know that that's energy essentially going out the drain, energy being lost to the air, but they're unsure, how can we capture that energy? How can we reintegrate that flash steam and that energy back into our system? Then third point that's also very common is the steam trap conditions. Sites can have 200, 300, 400, sometimes 10,000 steam traps on site. But very commonly as well, they're unsure, what's the condition of our steam traps? How much does a working steam trap leak? Because actually it's true, working steam traps also pass some steam as well. So how much is that costing us? And it's not often known. And then from a top level perspective as well, we get some energy saving goals. Many sites, especially nowadays, it's great to see they've got carbon emissions targets, net zero targets, and energy emissions goals, but it's sometimes difficult to find areas where can we start on this journey. So our advice in any kind of steam system analysis is to kind of split it into two to help fragment the issue. Firstly, looking at reducing losses from the live steam system. And that's something we covered in a bit of detail in the previous webinar from A2EP. You can catch the recording online. That's where we're talking about steam traps, steam trap management, and how we can make sure that we're not losing steam from our live steam system. Our focus today is going to be on the condensate system and how we can make sure that we're capturing absolutely as much as we can waste heat from that condensate system. Primarily, first point of call, and we saw it on Alan's side as well, the potential of just recovering condensate in the first place. So we're going to start with a case study. We've got 2 case studies today, both at the same site, a major global food manufacturer in the Australia, New Zealand region. This is very common across many sites at this kind of situation. So it's a general diagram, not an exact one. A general diagram where there's a steam heat exchanger, maybe for a CIP process, a clean in place process, where they're preheating that cleaning fluid with steam up to some set point between 50 to 90 degrees. And then very commonly, because that set point is less than 100, we get a situation where we have a very low pressure within the heat exchanger, and then the steam trap basically has a very low pressure going into it. And then typically that pressure is not enough to push that condensate all the way back to the boiler area. And as a result, we get condensate backing up into the heat exchanger, which is unacceptable. The site needs that heat exchanger to work. They cannot accept condensate backing up, so they'll open a bypass valve, and instead of returning that condensate, it'll be dumped to the ground. Very common situation. From a process perspective, that's absolutely fine, because at the end of the day, they need that heat exchanger to work. But we need to highlight the energy loss associated with that. Not to mention, the second issue is that even if there was not a pressure issue, returning the condensate imposes some risk on the boiler system, because if this heat exchanger were to rupture because of water hammer or corrosion from backed up condensate, they could get the CIP fluid, those chemicals going back into their boiler system, which is another risk that the company, the site, could not afford. So the solution should be split into two phases, and that's what was done on this site. Some images there to show some of the installation. So the first issue is the fact that we do not have enough pressure to return the condensate. So that's an independent issue on its own. And the solution is very clear. It's not just TLV who do this. Many manufacturers have mechanical pumps or pump traps that are designed to discharge condensate when there is enough pressure naturally. And when there's not enough pressure, they'll collect the condensate and use higher pressure steam to push that condensate all the way back to your feed water tank. Very common solution, very well established in the industry. And the key message there is that where you're not returning condensate, explore the solutions that might be available to allow you to return that condensate without affecting your heat exchanger or your application, because that's always going to be the priority. A solution that affects your heat exchanger is not a solution at all. But then the second issue is, how do we deal with the risk of contamination? And that's with water quality monitoring. So even applications which have previously been earmarked as these are impossible to return condensate from, we believe that there's always some negotiation that can be done with site, or some discussion that can be done. And in this case, site installed these turbidity sensors, which will measure essentially the cloudiness of the condensate and measure the impurities of that condensate as it's coming back to the boiler house. If it surpasses a predetermined level that we say we're not happy with this level of contamination, then no problem, it'll dump the condensate, which is what they were doing before. But in general, most of the time, so 80% of the time or more, it was clean. It was deemed clean enough to return to the boiler, because it's only an issue if there is a rupture in the heat exchanger anyway. So implementing this across site, we can see some of the pump sets over there, took the condensate recovery rate up to 80%, also eliminated water hammer cases in their heat exchanger, and prevented or mitigated the risk of cleaning liquid contamination. And we'll discuss detail about the payback period a bit later, because there's a second project on this same site. It's all well and good talking about condensate return like it's, the easiest thing to do. But I want to talk as well about some of the challenges with that. So typically, condensate return, we look at open systems or closed systems. Today, we'll be talking about open systems, which is where a site might have condensate collection tanks strategically placed around their site, where the steam traps can discharge into, and then there'll be an open vent to make sure there's no back pressure. And then that'll get pumped back into the boiler system. The alternative is a closed system, which is a heavily engineered design, but highly efficient. It's certainly possible on a few sites, but it needs a detailed engineering review, because essentially you're putting back pressure on all of your equipment. But the trade-off is you have no vents, except for the pressure control, pressure safety vents in your system. So you can return very high temperature condensate directly to the boiler. Usually in an in-person seminar, I ask everyone, okay, how much steam do you think that is? This is a typical image of a steam vent coming out of a condensate recovery tank. I'm not going to wait for feedback on this one, but if you want to guess, please look away now. That's how much steam is coming out of this vent. This is measured in a TLV factory in some experiments that we were doing. And then the cost of that vent, that amount of steam going out, if this were a site event that you see less than half the year, is just over 80,000 Australian dollars. And what that constitutes of is residual heat that's being lost in that steam, but also the water that goes into that, not just the water content, but the wastewater treatment costs as well that go into that, and the carbon emissions that go into the whole water source process. This is all water that you need to replace. So that's why the cost is typically quite high. So whenever we see vents like this, we need to think about, okay, how can we capture these vented losses best? So we've got two case studies here. The one on the right-hand side is in that food manufacturer, and the one on the left is a general diagram. One is where we've got condensate tanks and steam being vented out of the condensate tanks. Again, very normal. As long as it's not affecting our process, it's no direct issue. However, this is definitely an energy loss, which the site was interested in recovering. And the second case is where we have boilers and their blowdown systems losing a lot of heat. So in this case, this is the one in New Zealand. They've got about 450 kilograms of flash steam being lost from their blowdown water, not to mention the very hot blowdown water as well going down to drain, which they need to cool down before they can send it down into drain for legal reasons. Overall, the blowdown situation, you can recover that blowdown heat with heat exchanger, atmospheric heat exchange, and I'll explain why it's very important it's atmospheric in a minute. And in this case, they managed to preheat their soft water going into the deaerator with that waste heat all the way up to 95 degrees compared to before where it was 42 degrees. So a massive saving for site in terms of reducing the amount of steam they needed to preheat their soft water. Overall, this step and the condensate return case study we saw before was about 400,000 Australian dollars savings on that site. And then the other case is a very similar heat recovery unit, an atmospheric one you can also use on flash steam. This site used it to recover just the energy from their flash steam onto a nearby hot water user with a payback period of about 1.1 years, just over 1 year. And then this is an image of the heat recovery units. Just to make a quick note is that these heat exchangers, is absolutely critical that they are putting no back pressure whatsoever on your processes, because if you put some back pressure on this condensate return tank, suddenly your process is affected. Same thing with the boiler. So sorry for speeding through that. I'll just do 3 points, and we've got some further case studies there at the bottom. As mentioned, reducing losses can come from the live steam system or the condensate system. Always start by trying to maximize your condensate recovery rate before recovering the further losses. Vented losses can be recovered, and there's also always potential for further optimization if you've done those first 3 points, whether it's closed condensate recovery systems or self-circulating systems. We've got a little diagram there that you can peruse at your time. I'll look forward to questions on the chat or in the Q&A section later on. Thank you all very much for your time.
Great summary. Thanks for that, Elsadiq. Lots of tips there. Plenty of actions to do there, Mark, to get to best practice.
Absolutely. Yeah, thank you, Elsa. Next up is Nick Holmes from Windsor Engineering. Nick is General Manager for Windsor, General Manager Australia for Windsor, and is a seasoned mechanical engineer in industrial engineering in both Australia and UK. For the past 20 years, he's been with Windsor, where he focuses on large-scale thermal energy systems, including renewable energy boilers and specialist heat recovery technologies. Nick is certainly one of those people that hates waste energy, and he's got a lot of experience at doing something about it. And we're about to hear some examples.
Thank you, Mark. Appreciate that. Thanks for having me here. So as you said, yes, Nick Holmes, I'm General Manager for Windsor in Australia. We're a fairly diverse engineering company that's backgrounds within heat exchangers. We started life with timber drying kilns, fans and filtration. That's the sort of heart of what we do. And it's all about heat, generating heat, transferring that heat into useful applications. The other side of the business is a dedicated boiler business, biomass, electric boilers, air heaters. So it's a bit of a flavour for what we do. My background is with boilers, but I look after a heat exchanger business here in Australia. The heat recovery, that's what this is all about. We focus on a certain type of heat exchanger. There's probably 3 main generic sort of designs that are used in heat recovery. One is shell and tube, pretty well known in Australia. They're typically for sort of steam applications, steam to fluid, change of phase. Typically, they can be used for a gas cooling or gas heating. Then there's the plate type heat exchanger. They're typically fluid to fluid. So if you've got a water stream that you want to create hot water from a clean stream, that's the sort of focus of a plate heat exchanger. What I'm going to pursue today is purely a thin tube type heat exchanger. It's predominantly used for heating or cooling air streams, process air. They can be used for slightly different applications, but nearly always they're using a heating medium like hot water or chilled water or possibly steam to add heat or to recover heat from a gas stream. And when I say gas, it might be a clean air process or a dirty exhaust from a dry process of some sort. So there's two main technologies that go into these heat exchangers. There's a traditional thin tube that people probably have seen around. Typically, that's an extruded fin, so you might have an aluminium fin on a base tube that be either stainless steel or carbon steel. So that's the photograph in the right, and typically that relies on mill manufactured lengths of tube. Whereas on the left, a fin pack. Some people call it a plate fin. Yeah, it's similar to a car radiator if you sort of think of it like that. So there's a lot of heating surface in the same face area, so they're typically more efficient than a fin tube. There's lots of flexibility in the design in terms of materials for the fin, the materials for the tube. So that top photograph shows you press the fin out of a solid piece, so it's a more robust solution than a traditional fin tube. So probably the key bits of information to consider when you're designing a coil is what is the exhaust stream that or the waste stream that you're looking to recover. Has it got particulate in it that might foul up a heat exchanger? Has it got chemicals or acids that could corrode the materials? So material selection is key to that. What sort of back pressures can it accommodate? If you've got a sensitive process like a reciprocating engine, they're very sensitive to having additional back pressures on them. So you may struggle in certain applications to put a coil in that kind of scenario. And yeah, what are the temperatures that you're trying to achieve in the fluid? In this instance, if you're recovering exhaust gas, putting it into hot water, what are the peak temperatures of the exhaust? And the closer you get to the pinch temperature of the fluid, the harder it is to recover that energy. You need more heating surface, and it's diminishing returns. So there's always a sort of sweet spot of the design. So really today is just about some examples of what can be done, what we have done in recent years. There's just an array of different photos here to sort of put it into the perspective. So the middle ones are, so in the middle at the top is a 30 megawatt economizer for a boiler. The one below that is a primary and secondary economizer application. We'll go into more detail in that one in a couple of weeks, actually, if you're sitting in on the boiler specific. This is a large steam air heater, typically used in a powder spray dryer where they need a lot of high temperature steam high temperature air for the process. So you need 200 odd degrees in air temperature, so you need high pressure steam to generate that hot air. But you can put a heat recovery coil in the exhaust, and we'll cover that later, how that can reduce the steam demand. This photograph it's a solid model, sorry, of a new development is where we link a heat recovery coil in the exhaust stream. This is a process heater, a gas-fired air heater. So there's a flue gas typically here. We put a heat recovery coil in this section to recover some exhaust heat, and then a simple water loop with a pump to a secondary coil, which is an air preheater. So again, it's a simple closed loop system, recover some heat, put it back into the process air to add up to 7% efficiency to the heater. So there's 3 or 4 specific case studies here just to give an overview. Typically, economizers are used in boilers, has been for a long time, but they're limited to how much heat you can recover because they're preheating your feed water. So the feed water temperature and the flue temperature get to a similar balance. You can't drop it any lower. You can't drop the exhaust temperature any lower. But with an additional heat recovery coil, heating an alternative heat sink, you can drop your flue gases significantly lower. So in this instance, a 30 megawatt boiler, it's a biomass boiler. The standard flue temperature is already low at about 140 after the economizer and an air preheater. But we managed to drop that down to 125, which doesn't sound like a lot, but with a 30 megawatt exhaust stream, that's a lot of energy. So this application, we recovered 2 megawatts, 2 megawatts of medium grade hot water that could be used in the process. So, excuse me, yeah, the coils, they were big coils. You can see from that bottom photo, that's one of the 2 coils. There were 2 stacked on top of each other, approximately 2 meters by 3 meter face area. They probably weighed close to 2 tons each. So we're talking about a lot of stainless steel. This was a semi-condensing application. So burning biomass that's got a lot of water in it, the water passes through the boiler and it's a water vapor that's then passing through the stack. So if we can utilize some of that latent heat, you get extra bang for your buck in terms of condensing that water out and recovering the energy. So that's at the sort of large end of what we can do with heat recovery. The same technology at a much smaller scale. So this is a major food and beverage player actually in New Zealand on the back of a fire tube boiler, a 1200 kilowatt gas-fired boiler. A little bit special. There were some real constraints on physical footprint. So the heat recovery coil was mounted vertically with a stack sitting above it just because of footprint. So recovered the 220 degrees stack temperature using low temperature process water at 15 degrees. We could drive that stack temperature down to 70 degrees. So it was not fully condensing, but there's a lot of condensation happening in that flue gas stream. And with the reasonably high water flow, we got that water temperature up to 47 degrees. There's always a trade-off with if you want to get a higher water temperature, it would reduce the water flow rate, and you'd probably need to put more heating surface in there as your pinch point gets closer. So here we've got the disparity between the 70 degrees is the outlet temperature and 47 of the water. As if you're trying to get a higher water temperature, you just need more heating surface to get there. This one was a little bit special. It was a bit of an R&D opportunity to use some slightly cheaper materials. Typically, when you're condensing, you need to use stainless steel 316 to minimize the corrosion effects of the condensing flue gases in that stream. But we actually used part of it was an epoxy coated aluminium. So aluminium's got the benefit of a much better heat transfer material, but it is more susceptible to corrosion. So this trial's been going 3 years and it's held up well. So it's giving us some comfort that we have got a lower cost solution there for longer term that can be put into the market. So yeah, down the bottom, as Elsa mentioned earlier, most boilers have a stack temperature close to that 150. But with having an external process stream of water that can be used, you can significantly improve that efficiency up to another 3 or 4%. Does rely on having that additional utilization, whether it's CIP water put into a storage tank. The challenges are always what's the boiler load like compared with the external load? Will they work in sync, or do you have to have a big buffer in there to accommodate it? Slightly different opportunity here was again in some large pulp mills in New Zealand. there were actually 3 different sites that had the same problem, with low-grade steam being wasted from the refiners. It was contaminated steam, very low pressure, and most of it was being exhausted to atmosphere. So we came up with some concepts, and those concepts turned into sort of feasibility, and then all the way through to a turnkey installation over time. But again, a significant amount of energy recovered, 3 megawatts from very low grade steam at it was about 110 degrees, I think, just under 1 bar. Quite a complex project because there was some contamination both in the steam, and it was quite a difficult site with dust fibers. So the solution needed to accommodate both of those. But it offset LPG, so yeah, it's quite old now, but back in its day, even with lower LPG prices, it was about an 18-month payback for that turnkey project. A big area we see that there's some real potential in both Australia and New Zealand is in the dairy plants, where they have significantly large thermal energy demands in their spray dryers to turn the milk into powder. Typically they use, so this project, approximately 20 megawatts per dryer of thermal energy. It needs that high temperature to achieve the 220 degrees process air temperature into the dryers. And then the exhaust of that is relatively low. They're exhausting to atmosphere about 80 degrees, so it's already pretty low grade exhaust temperature. But because of the high mass flow, there's still a huge amount of energy recovery that can be pulled from that. So the calculation showed there's a megawatt of heat from each of those dryers out of those stacks could be recovered, and by putting a water circuit in to an air preheater, the air preheater would utilize 55 degrees of water to preheat the process air, and utilize that 1 megawatt of energy. Obviously a significant project to execute something like that, but we ran a trial in conjunction with one of the universities in New Zealand, and that's what this photograph shows. We pulled out a small component of the exhaust gas, put it through a small coil that you can see in the middle there. It's actually 2 coils to allow as much heat as possible to be recovered. We were condensing the moisture in the air there. One of the biggest risks that the end user saw was the fouling contamination of that coil with the small amount of particles that come through from the spray dryer. But this proved that wasn't the case. It was actually sort of self-cleaning. The semi-condensing nature of it meant that it was washing away any of the powder that collected. So it ran for a full season, proved its purpose. The hard thing to get these projects off the ground is the top of a spray dryer, specifically in New Zealand with seismic constraints. A big coil is a lot of weight, hasn't been designed to accommodate that. There's a lot of piping to get that hot water down into the preheater coils, the steam coils, the air heaters. So there's a lot of logistics to make it happen. But in theory, it's all doable. Probably for a new build, it would go without saying this would happen. And probably a bit of a plug there, Jared, that you'd like. We are seeing the applications where if you can recover the low grade heat, you can then couple that up with a heat pump to lift that temperature to again make it much better to preheat that steam coil that's using either gas or coal to generate the thermal heat they need. So it's the way to go in the future. So that's it for me. Yeah, hopefully it's given a few ideas and a few thoughts to what can be done. Back to you, Jared and Mark.
Thank you, Nick. Another 5 or 10% saving in energy right there, all with good ROI. So we're certainly adding them up as we go through these presentations. And Mark, final presentation. Who have we got? Alfa Laval. What? Just on mute there, Mark.
Yeah, thank you, Nick. That was great. Next up is Anson John he's from Alfa Laval, Technical Sales Manager. Anson brings 20 years of experience delivering heat exchanger solutions across a wide range of sectors, including power, mining, ventilation, data centers, refrigeration, and HVAC. Anson's based in Melbourne and helps clients with smart heat recovery solutions. So over to you, Anson.
Thanks, Mark. I hope you can see the slide. Yeah, so as Mark said, based in Melbourne, sunny Melbourne, responsible for gas grid and brazed heat exchangers business across Oceania. So most of you know how the heat exchanger works, a plate type, heat exchanger works, but I just would like to show you a working principle of this heat exchanger. So I got nuts and bolts and plates, and the hot inlet and the cold inlet on the other side. It's always counterflow because that's best for the heat exchange. It's very efficient. So this is how it looks pretty simple, but there's a lot of R&D and engineering has gone behind this. So I'm just I would like to talk about a few applications where we are predominantly working in this food and beverage industry for recovering the heat. And this is a typical example. If you are, would like to do a heat recovery from hot oil in an air compressor. You can, in the schematic, you can see that, you got a screw air compressor, and which is producing hot air at 95 degrees C. And of course, it carries some oil, and that oil is separated in the oil separator. It goes to the oil cooler. Then with the cooling tower water, it is cooled, and that cooled oil is going back to the air compressor. That's pretty normal. And what we are suggesting into the market is to add a plate type heat exchanger to do heat recovery from this hot oil, which is at 95 degrees C. So you can see that you can have a piping to keep inlet to a plate type heat exchanger, 95 degrees C, and then you can heat up the water from 30 degree to 60 degree or even higher, which can be used in different applications. And that also will reduce the size of your oil cooler and also the size of the cooling tower. So that's additional advantages. And on a Alfa Laval has got a pretty good return on investment calculator, which is pretty smart. So I've done some data here. So you can see if you got a 95 kilowatt air compressor, which is having a 95 degrees C of air leaving, and which let us assume that it's working 12 hours in a day with a 30 days, 12 months. So if you are adding a oil cooler plate type, the approximate price of this heat exchanger is at around 8 grand. And with the installation and other pipings will be additional 8 grand. This is considering higher labor cost in Australia. And with a cost of energy of 70 cents and so on. So if you are heating up the water from 30 to 60 degrees C, we are expecting a payback period of 8 months, which is pretty impressive. So it's not only the cost saving. Of course, we are saving on the CO2 emission, which is around 263 tons per year. That's also significant. And it's pretty straightforward. So this is something we should be thinking in our mind about doing this. The other thing is that heat recovery from flash steam and subcooling. So you can see here, you can do a lot of heat recovery from the flash steam, which is at 104 degrees C or 1.2 bar pressure. And you can easily heat up the tap water from 10 degree to 60 to 80 degrees C, depending on your application. And this is getting pretty popular. We are working closely with different companies, engineering companies, to do this. And I have not done a return on investment calculation here because it really varies, but we have seen that the return on investment is close to 2 years or slightly more or less, depending on the application. So it's pretty interesting. And this is, I mean, since we are all, most of us are working in the, food and beverage industry, I understand. So most of us will have the industrial refrigeration plants, or even commercial refrigeration plants. And there is a lot of heat recovery possible in the refrigeration plants. And you can add a de-superheater in a compressor discharge line. You can do the heat recovery from the hot oil from the compressor. You can add a liquid subcooler, and you can generate hot water from plate type condensers. That's getting pretty common. And it's if you ask me that in New Zealand, this hot water generation from plate type condenser is pretty common these days. So have done a cost saving analysis by adding a de-superheater. Suppose if you got a 1 megawatt ammonia refrigeration system, which will have ammonia flow rate around 0.23 kg per second, and if you got a piston compressor at the site, which generally it has got a discharge gas temperature of around 110 degrees C, it can go up to 150. And if you have a condensing temperature of 35 degrees C, and let's take de-superheater effectiveness as 70%, then based on a simple calculation, we all know this formula Q equals MCP delta T, so around 30 kilowatt. And if this system is working for 6,000 hours in a year, we are talking about 180,000 kilowatt hour per year. And with the 70 cents per kilowatt hour, we are talking about a saving of $126,000 in a year by installing a de-superheater. And to install a de-superheater, the plate type heat exchanger will cost around $10,000, and maybe the additional, the piping and labor cost additional $10,000. So we are talking about a $20,000 investment and saving a big bucks. At the same time, when you have a de-superheater in the system, of course, your condenser can be much smaller because your inlet temperature to the condenser is going to be pretty low. It's not going to be 110. It's going to maybe 50 degrees C or something. So that's another saving. And since you are not going to have a high inlet temperature into the condenser, the scaling in the condenser will be much lower. So we are talking about much saving on the maintenance of the condenser as well. So there is a lot of saving there. And if you have annual cost saving from a heat pump, if you got an existing industrial refrigeration plant, and by adding a condenser, if you got a piston compressor there, the ammonia discharge gas temperature can be up to 120. Even we are designing for 150 degrees C, as I said, and you can set the condensing temp of 87, which will help the customer to heat up the water from 20 to 85 degrees C. So that's, and with a very close temperature of like 2 degrees C difference between the water leaving and the condensing, the system COP can be 5 almost or higher, and that will bring a lot of savings. And as compared to hot water generated by the boilers, it's going to be at least 20% of energy saving it's going to bring. CapEx is going to be a bit higher if you're going for a new heat pump, but if you got an existing refrigeration system with a piston compressor, it makes a lot of sense to add a condenser, which can work at a high condensing temperature and generate hot water from the system. Yeah, so you heat recovery from wastewater. This is something which we do especially in the pulp and paper industry and also some beverage industry. So if you got effluent, which is high degree water like 60 degree, 50 degrees C, of course, rather than that wasting into the drain, you can do a lot of heat recovery from that. And one of the biggest challenge the industry is facing when you recover heat from this effluent is that the particles present in the effluent that can create some sort of fouling in the plate type heat exchangers. But to counter that, we are using, we call wide gap plate heat exchanger. So which has got the pressing depth in the plate is bigger, like 8 mil or close to that, and that will allow a lot of particles to pass through the plate type heat exchangers, because in the plate, that it's not laminar flow. Most of the time it's turbulent flow, so the particle doesn't stay. And at the same time, you can also use some filtration to take out bigger particles than that. Using a spiral heat exchangers also make a lot of sense if you got bigger particle sizes. And these are, pretty common application which we do. And we have got small boys we call braze type heat exchangers. So we call this gas to liquid. So you can see it's a braze type, stainless 316 and copper brazed. So we also got the same product in complete stainless 316. So you got the bigger pots here, which is for the gas flow, and the smaller pots for the water. So you can do a lot of heat recovery from the flue gas through this small heat exchangers. So these heat exchangers are good up to, it's not for a big application, but if you got flue gas of 2000 kg per hour or even up to 3000 kg per hour, you can use this to do a lot of heat recovery. We had done a project in Australia in a food company, like they had a flue gas coming in at 80 degrees C, and we were heating up the water from 15 degrees C to 65 degrees C using this small one. And if the flue gas getting condensated, of course, we got a drain point here, which you can drain out. The project which we did, the customer was getting around 2000 liters of fresh water in every 2 weeks, which was like a byproduct. And the total investment was like $16,000, including the installation charges. So this is pretty smart, very compact. Yeah, so this is something which we do in the market as well. Yeah, that's all from my side today. Thanks.
Good one. Thanks, Anson. That rounds out those technology options really well. I will note, I think that we have to look at that calculation for the de-superheater, the dollars for 70 cents a kilowatt, probably a bit high for gas, but no matter what, I think it's going to be a good recovery there, but worth might have to check some of those numbers. Mark, we've got a fair few questions and things coming through. Maybe worth just reading out a few questions and answers there from the chat or something.
Yeah, sure. We've got one from Steve Edwards addressed to Elsa. It's a long one, and I'll read it out. I often find that boiler house and blowdown are quite remote from the site or the usage point for recovered heat. Hence, unless blowdown processes are uncontrolled, manual, or appear wasteful or large in size, I will ignore this as an opportunity. Do you ever look at a blowdown and say, don't bother? Do you have some kind of minimum concept of viability for a blowdown recovery based around size, frequency, and distance?
Yeah, great question. To be honest, it should always be a consideration of is it, number one, is it worth recovering this heat with all the process changes you might have to make, but also is there a feasible heat sink nearby? And you're absolutely right. And yeah, in many cases, the boiler house is quite far removed from the rest of the plant. But you'll always have your feed water tank at least there, and if that feed water tank can take any extra heat, or if it's an atmospheric tank, there are some cases as well where you can pressurize that tank so it can allow the recovery of more heat into that feed water tank. But I think, yeah, it's very reasonable to say there are some cases where your heat recovery in the boiler house is tip top and there's no heat sinks nearby. So sadly, that water does, it does, and that energy does need to go if there's no suitable heat sink.
I think I'd add to that one, Mark, we've got to consider maybe a future gas price or think of something, maybe a carbon price in there as well. At $10 a gigajoule, there might be X cases and might be only, it might be if it needs to be less than 100 meters away, but what's over at $20 a gigajoule and a carbon price? Okay, well, maybe it's still economical to do something at 200, 300 meters away. So more there. What else we got there, Mark?
So I think that's all the questions in Q&A. I've got some webinar chat questions, which Nick, I think you've answered quite a few of them already. There's one here from Jason to Anson. Anson, do you have some rules, typical rules of thumb for approximating the cost of various heat exchangers?
It's pretty hard, the rule of thumb, because heat exchangers, it really varies based on the flow rate and the temperature difference and the pressure drops, and how much. So it really, unfortunately, there is no rule of thumb, I would say. But if you can reach out to me direct to that, we can run different simulations and see how the price works out. But yeah, it's unfortunately there's no fixed rule for the price. Yeah.
Thank you.
That's it. And
Yeah.
maybe Nick would like to expand on a few responses you put in there on and back pressure and carbon steel for some of these heat recovery options.
Yeah, there was a question just are there any limitations to materials? Reciprocating engines are a little bit unique on recovering heat. I think there are very bespoke solution providers, especially from Europe and the States, that do dedicated units for that, just because they're so susceptible to back pressure constraints on the engine. But in theory, yes, we can. It just means it's got to be a big coil to minimize what that back pressure is, and then it's just whether economically it works. In terms of materials, yeah, carbon steel is certainly an option. There was another question I maybe didn't answer about the condensing side of things. Certainly, if you're getting the exhaust temperature down below the dew point, which with a gas boiler might be in that 135 kind of range, everything downstream of the coil needs to accommodate condensing. So it's got to be stainless steel. So that big 30 megawatt boiler, yeah, all the flue gas ducting, the stack, and I think there was an ID fan downstream as well that needed to accommodate that those materials. Typically 304. Possibly the coils are nearly always 316. That's our standard.
And I'll put it to the panel here a bit. There's quite a few options here, and I'd suggest when things were first done, Nick, these dryers here at $10 a gigajoule for gas, and now we're at 15, maybe 20, maybe 25. And a lot of retrofitting. How do we get people to relook at this and say, run the ruler again on these heat recovery options, maybe now with that higher gas price?
Yeah, that's probably what it is. That it's run it again, see what the economics look like. Yeah, typically 2 years was a typical sort of payback project for a lot of these small, medium-sized heat recovery. We're seeing the trend that more people are putting economizers on smaller and smaller boilers now as the economics do stack up. So yeah, agree. It's just ask the question, what are the economics payback looking like?
Good.
I think that's the end of the list of questions, but if I've overlooked something, I'm sorry, maybe repost if necessary.
Mark, I think there was a question regarding a percentage saving from the case study that I presented, which is the McCain's Barra site. But the message was gone. I think it might be deleted. But I just want to say that McCain has advised me not to disclose the exact gas usage or percentage saving data. And I think that there are a couple of representatives here on the call as well from McCain. So, but given it's a 25 megawatt boiler, what the gas saving as in numbers, you can potentially back calculate roughly what the percentage looks like. But I'll just leave it there.
Nice work. All right, Mark, thanks very much for that. I think we'll wrap it up. I think we gave an excellent summary there of being able to save that 20%. As we often say, if you can't find 20% of energy savings, look harder. And I think some great examples there with really good ROI as well. So thanks very much for our presenters, Alan, Elsadiq, Nick, and Anson. Just to wrap things up, give you all a bit of a flavour of what's ahead. We've got 2 more of these webinars coming up, one on steam boiler optimization and one on metering and monitoring. in just tomorrow. We're down in Melbourne on a member mixer. We're going to have some fantastic presentations from members there, as well as we have Victorian government coming along, telling us and listening a little bit about what our thoughts are, say, on this Energy Innovation Fund. They'll be probably just repeating what's available on the website there, but we'll at least get an opportunity to say this is what we're hoping to see from this $10 million fund, and maybe get a chance to get help with some design work on that one. Also to mention that to hopefully people have seen that there's this new fund from New South Wales government now up to $30,000 covering some of these costs. And hey, you could look at heat recovery when you're looking at these studies as well at the same time. And so they'll be presenting at the member meeting tomorrow. We're all leading up to getting excited about the heat conference, getting about a month away now. We've got some fantastic presentations coming from so many different end users. The Tees group is going to be telling us about their biogas. We've got the Kilcoy Foods group telling us about their biomass project, and lots of end user presentations with case studies. So that's going to be a fabulous conference, and so hope you can all join us there at the end of August. If you do want more A2EP, as always, follow us on LinkedIn. You'll see lots of posts there and lots of updates on latest technology and projects that's happening. And all that's left to say is thank you very much for joining us today, and hope to see you at our next webinar. Thanks for our presenters, and thanks for joining us today. Thank you. Bye.